Good day, grade 10 science students. Today this lesson is about balancing chemical equations. What we're going to do is divide this up into 4 parts to make it easier on you. We're going to learn how to make a word equation, which just involves making equations with words. We're going to make something called skeleton equations, and we're going to talk about the law of conservation of mass, and we're going to eventually learn how to balance chemical equations, but we have to do those other things first. So let's start with making a word equation. So a word equation is a type of chemical equation that really shows it basically has reactants on the left and products on the right, but it involves words. For example, if we take a look at something like hydrogen plus oxygen makes water. Now you notice that I said, instead of saying this arrow, I said makes. Well, really what we're saying is it produces water. So the reactants are hydrogen plus oxygen, and the products are water. So again, the reactants are going to be on the left and the products are going to be on the right. Now this is words, so this is a word equation. What we want to do is eventually turn this into something called a skeleton equation, which shows the chemical formula. So if we're going to make a skeleton equation, we'll replace those chemical names with chemical formula, and we're still going to have an arrow that means produces between reactants and products, and we're also going to put in something called symbols, where you have a little G, which will represent gas, L, which will represent liquid, S will be solid, and aqueous will mean dissolved in water. So let's do that. So I'm going to take my hydrogen plus oxygen, I'm going to turn it into water. Take a look at the symbols that I've produced to make something called a skeleton equation. So this is an example of a skeleton equation. I have H2 plus O2 equals water. Now I know water is a liquid, so I'm going to put a little subscript L. Subscript means lower. Okay, lower to the left. Now we know oxygen is a gas, so I'm going to put a little G, and I'm going to put a hydrogen, I'm going to put a G as well. Now you're not expected to know that, but those are describing the states of hydrogen, which is a gas, oxygen, which is a gas, and water, which is a liquid. Now this is known as a skeleton equation because it's considered to be unbalanced. So what does that mean exactly? Well, if you count the number of atoms on each side of the skeleton equation, you'll see that it's unbalanced. For example, so let's take a look at this again. So here's our equation again, but if we take a look, what's unbalanced about it? Look at the left side of the arrow, which is considered to be my reactants, and the right side of the arrow, which is considered to be my products. You can see that I have 2 hydrogens here in the reactant side, and on the other side of the arrow, I have 2 hydrogens as well. That matches up. That's not a problem. So if you start with 2 hydrogens and you finish with 2 hydrogens, you know, that's a good thing because you started and finished with the same. If we look at the other side, we have 2 oxygens on this side, but only 1 oxygen on this side. This means that it is unbalanced. You started with 2 oxygens as reactants and you finished with 1 oxygen. Now this is a problem because it breaks something called the law of conservation of mass. Now this means if you start with 2 hydrogens and you finish with 2 hydrogens, this is great because that's going to weigh the same. But if you start with 2 oxygens and you only finish with 1 oxygen, so you start with 2 and you finish with 1, that means you lost an oxygen. That means that this side would weigh less. The product side would weigh less, which means you break the law of conservation of mass. So the law of conservation of mass is basically this. The mass of products must equal the mass of reactants. Now you should have seen this in the lab that we did before this. And another way of thinking of this is that the number, because atoms weigh the same, like an atom of hydrogen should weigh the mass of another hydrogen. So if you start with a number of atoms on the reactant side should equal the number of reactants on the product side, the number of atoms on the product side. And this is the law of conservation of mass. Like matter, atoms cannot be created or destroyed. Okay. So what we're going to do is we're going to take a look at another example. Actually, before we look at our next example, let's look at this here. So we knew that we destroyed one of these oxygens here. So what has to happen to balance this is we'd actually have to change this to say that we need 2 waters instead of just 1. Now we have 2 oxygens, and this coefficient, this is called the coefficient it multiplies in. So you have 2 oxygens now, but now you have 4 hydrogens. So I'm going to put a 2 in front of here as well, and now it's balanced. So there's 2 times 2 is 4, 2 times 2 is 4, 2 times 1 is 2, and there is 1 oxygen molecule here times 2. So I know this is difficult to see yet, you probably don't understand this quite yet, but we have to change the numbers in front of the molecules. Let's take a look at another example here. If we look at the amount of atoms on both sides, there's 3 irons on the product side, but only 1 on the reactant side. 2 oxygens on the reactant side, but 4 on the product side. So you're changing the amount of atoms when you go from the right side to the left side. So what you have to do is you have to change the coefficient that's in front. And I know I just showed you the answers there. I'm going to do it by hand though. To change this, you have to figure out, okay, I got 2 oxygens on this side and 4 on this side. I'm going to take a 2 and put it in the front, and it ends up multiplying in, and now I have 4 oxygens on the left hand side. There's 3 irons, as you can see here, but only 1 here. And if there's no number in front, that means that there's 1 here, guys, and that gets multiplied in. So you have to put a 3 in front of this. And now we go from a skeleton equation, which is unbalanced, to a balanced chemical equation. So the numbers end up being there. To finish off the steps, we want to make sure that we have an equal number of atoms on both sides of the equation, just like we showed you before. And if we count them up, 3 irons on both sides and 4 oxygens on both sides, and that's it. We're going to try one more example. I'd like to see if you can balance this. Okay, here's another example. We have nitrogen gas plus hydrogen gas equals ammonia liquid. So what we want to do is we want to count up the atoms on both sides. So what kind of elements do we have on both sides? Well, you can clearly see, there's nitrogen on this side and there's hydrogen on this side, and those same elements are on both sides. Now when you have a skeleton equation, one thing that is in common is that it has a coefficient of 1 in front of all the compounds. What we want to do is we actually want to figure out how many atoms are there. So this is actually 1 times 2. So that means that there's 2 nitrogens. Okay? And here we have 1 nitrogen as well. So 1 times 1 here. There's a 1 here. Now on the other side you have 2 hydrogens and you have 3 hydrogens. So this is unbalanced because when you go from reactants to products for nitrogen, you go from 2 to 1. You destroyed one of your nitrogens. When you go from the reactants to products for hydrogen, you actually created hydrogen. So what I'm going to do is I'm going to actually show you what we call the Lewis structures of this, and let's just take a look at it to help us understand more. Okay, so I've actually drawn them out for you here, and you can see that you have 1 N2 here, 1 H2, and 1 NH3. So 1, 1, and 1. Now you'll notice that there's 2 nitrogens on this side and 1 nitrogen on this side. So this might be the first thing that we want to change. What we're going to do is we're going to put, you pick one, and it doesn't matter which one you pick. I'm going to change this to 2. You have to change the coefficients to whole numbers. So coefficients are the numbers that are in front, and they represent the amount of molecules that you have. And I'm changing this to 2. So now I have another ammonia on this side. And take a look how my numbers change. I now have 2 times 1, 2 nitrogens, which you can see right here. And how many hydrogens do I have? 1, 2, 3, 4, 5, 6. Okay. If we look on the other side, my nitrogen is now balanced with my nitrogen. I have 2 nitrogens on both sides. But what's out of whack? Well, what's out of whack is actually the hydrogens. You can see that you have 6 hydrogens on this side, but only 2 on this side. So what number do you think you can put here to change the hydrogens? Well, the answer is 3. If we put a 3, that means 3 times 2, which is 6. And now we are officially balanced. Take a look when I actually put 3 H2s. So that's 3 H2s. So that's 2 H2s right now, but 4 H's. And now I have 3 H2s. 1, 2, 3, but I have 6 H's there. It's now balanced. So we went from a skeleton equation to a balanced chemical equation that's not breaking the law of conservation of mass, because you're starting and you're finishing with the same amount of atoms. That's it, folks, for today.